Welcome, first-year med students, to today's Explainer. We're going to build the human heart literally from the ground up. Understanding the specific properties of cardiac muscle, like excitability, autorhythmicity, conductivity, and contractility, is absolutely foundational to everything you're going to do in cardiology. Today, we're going to trace the journey from microscopic cellular architecture and electrical wiring all the way up to the real-world clinical applications you'll be seeing very soon on the hospital wards.
Here's our roadmap for this explainer. First up, morphological properties. Second, autorhythmicity. Third, conductivity and action potentials. Fourth, mechanical and metabolic properties. And finally, we'll wrap up with clinical correlations.
All right, let's dive right into Section 1, Morphological Properties and Their Microscopic Foundations.
Take a look at this. Notice how the cardiac muscle fibers are striated? It's a lot like skeletal muscle, containing those familiar actin and myosin filaments. But here's where it gets really unique. Unlike skeletal muscle, these cardiac fibers are ribbon-like and highly branched. And brilliantly, where these branches meet, the adjacent cells are joined end-to-end by these dark, specialized structures called intercalated discs. These discs are vital junctions. They contain desmosomes that act like spot rivets to hold the cells together against immense mechanical stress. And crucially, they contain gap junctions.
Now, those gap junctions bring us to one of the most important concepts in all of cardiac physiology, the functional syncytium. Because gap junctions have incredibly low electrical resistance, they let electrical current flow effortlessly between neighboring cells. So, what's the result? Well, when one single cardiac cell fires an action potential, the impulse spreads so fast to all the other connected cells that the entire muscle mass becomes excited and contracts as a single coordinated unit. In cardiac physiology, this perfectly demonstrates the all-or-none law. If one cell is stimulated to its threshold, the whole syncytium fires. And because the atria and the ventricles are separated by a fibrous ring, they actually form two distinct functional syncytia. This lets the atria contract as one unified team, followed just a moment later by the ventricles as a second unified team.
Moving right along to Section 2, autorhythmicity, which is also known as chronotropism. This is essentially how the heart generates its very own beat.
To really understand how the heart sets its pace, consider this brilliant train analogy. Picture a train with 100 cars, and 3 of those cars are actually engines capable of moving on their own. One engine, representing the sinoatrial or SA node, can travel at 70 miles per hour entirely on its own. Another engine, representing the AV node, goes 50 miles per hour. And the last engine, the Purkinje fibers, goes 30 miles per hour. Now, if they're all hooked together, the whole train is going to be pulled by that fastest 70-mile-per-hour engine, right?
Looking at the actual physiological data here, the heart has specialized, non-contractile autorhythmic cells that depolarize spontaneously. But as you can see, they do so at different rates. The SA node has an intrinsic firing rate of 70 to 80 action potentials per minute. The AV node fires at 40 to 60, and the Purkinje fibers trail behind at 20 to 40. Because all these cells are electrically coupled, the SA node reaches its threshold and fires first, spreading the impulse and triggering all the other, slower tissues before they can even reach their own threshold. This definitively proves why the SA node acts as the heart's primary, normal pacemaker. It literally just overrides the slower inherent rhythms.
Okay, Section 3, Conductivity and Action Potentials. This is where we explore dromotropism and bathmotropism.
Now, what's really interesting about this slide is the incredibly unique shape of the cardiac action potential in a ventricular muscle cell. Unlike a quick nerve spike, there's this prolonged plateau phase right in the middle. This is called a fast response action potential, representing the tissue's excitability, or bathmotropism. And it's divided into 5 very distinctive phases, all driven by highly coordinated voltage-gated membrane channels.
Let's carefully step through the exact ionic mechanisms driving each of these 5 phases, because this is absolutely key. Phase 0 is the rapid upstroke, caused by a massive, rapid influx of sodium ions rushing into the cell. Phase 1 is a brief notch of early repolarization, largely achieved by the efflux of potassium out of the cell. Then we hit Phase 2, the unique plateau. This is a very delicate balance. Calcium is flowing into the cell through L-type channels, which perfectly balances the potassium that's flowing out. Phase 3 is rapid repolarization, where those calcium channels close and potassium efflux takes over to bring the voltage back down. Finally, Phase 4 is the resting membrane potential, maintaining a steady negative 80 to negative 90 millivolts until the next spark arrives.
But you know, the speed at which this action potential spreads, its dromotropism, isn't uniform at all. The incredible contrast here is the secret sauce. The conduction velocity in the AV node is extremely slow, just 0.05 meters per second.
This causes a crucial 0.1 second delay, which gives the atria time to completely empty their blood into the ventricles before the ventricles actually contract. Once past that bottleneck, the signal hits the Purkinje fibers, roaring ahead at 4.0 meters per second. This incredibly fast speed allows the entire endocardial surface of the ventricles to be activated almost instantaneously, ensuring a massive, synchronized pumping action.
All right, moving to Section 4, Mechanical and Metabolic Properties. Let's look at inotropism and the heart as an actual pump. So how does the electrical spark actually cause the muscle to physically squeeze? It happens through a really elegant mechanism called calcium-induced calcium release. This perfectly couples the electrical excitation to the mechanical contraction, which is the essence of inotropism. First, the action potential travels deep into the cell along the T-tubules. During that phase 2 plateau we just talked about, extracellular calcium enters the cell through L-type channels. Now, this small amount of calcium isn't enough to cause contraction on its own. Instead, it acts like a trigger. It binds to ryanodine receptors on the sarcoplasmic reticulum inside the cell, causing it to release massive flood-like stores of internal calcium. And it's this flood of calcium that binds to troponin, causing the actin and myosin filaments to slight and contract.
Now, the crucial point here is the refractory period. Unlike skeletal muscle, which has a very short refractory period, allowing for sustained, cramped contractions called tetanus, cardiac muscle has an unusually long refractory period, about 250 to 300 milliseconds in the ventricles. This long refractory period, which is caused by that prolonged action potential plateau, means the heart muscle absolutely cannot be stimulated again until it has significantly relaxed. Guys, this is literally life-saving. A tetanized heart would just lock up. It couldn't relax to fill with blood, and if it can't fill, it can't pump. Plus, this relaxation allows for the Frank-Starling mechanism. Basically, the more the heart fills with blood during diastole, the more the muscle fibers stretch, which leads to a much more forceful contraction.
Mechanically, the heart is a powerhouse, but metabolically, it is incredibly demanding. The heart has to contract repetitively for a lifetime without taking a single break, so it has a continuous, extremely high demand for oxygen. To keep up, cardiac muscle is packed with mitochondria, much more so than skeletal muscle. These mitochondria rely heavily on oxidative phosphorylation to rapidly synthesize the massive amounts of ATP required to keep the cross bridges cycling and the heart pumping. If oxygen is cut off, like during a myocardial infarction or heart attack, the heart muscle is rapidly damaged and fails.
And that brings us to Section 5, Clinical Correlations. Let's take all this basic science and ground it right into real-world practice.
When the cellular environment gets out of whack, the clinical effects are often catastrophic. Since potassium dictates the resting membrane potential and repolarization, alterations in extracellular potassium, whether it's too high or too low, can cause lethal arrhythmias, total loss of excitability, and cardiac arrest. Calcium is equally vital. Because of that calcium-induced calcium release mechanism, very high extracellular calcium can actually induce cardiac arrest in systole, literally locking the heart in rigor. On the flip side, removing calcium decreases contractile force until the heart completely arrests in diastole. You're going to be monitoring these electrolytes daily on the wards for sure.
Bringing it back to our train analogy, what happens clinically if the SA node, our 70-mile-per-hour engine, derails or fails? Well, the functional syncytium and the backup pacemakers step in to save the patient's life. The slower AV node simply takes over, driving the heart at 40 to 60 beats per minute. But this slower rate often leads to the patient feeling weak, developing heart failure, or even becoming comatose. In these cases of SA node failure or heart block, clinical intervention is required. We surgically implant an artificial pacemaker that rhythmically generates impulses, stepping in as the brand new engine to drive the whole train back at a healthy 70 beats per minute. So, when you see a patient on your cardiology rotation with an impossibly slow pulse or a completely chaotic ECG, I want you to trace it all the way back down to the cellular level. Think about those intercalated discs, the action potential phases, and the calcium stores. If a patient's SA node engine derails, what happens to the rest of the train? Well, you now know exactly what happens, and more importantly, you know exactly how the interventions you'll learn in the coming years will step in to save the journey. Keep this foundational knowledge sharp, and I promise you, the complex clinical cases ahead will all make sense. Thanks so much for learning with me today, and I will see you in the next explainer.